Picture standing at the edge of an infinite abyss, a place where the laws of physics twist and time itself slows to a crawl. Before you stretches a void so dense, not even light can escape its grasp. This is the event horizon of a black hole, the universe's ultimate cosmic mystery. These monstrous gravitational behemoths hide secrets that defy our understanding, bending reality in ways that seem ripped from science fiction. Yet, black holes aren't just mind-bending theories, they're real, lurking in the darkness of space, shaping galaxies and rewriting the rules of existence. What if I told you there's far more to these cosmic titans than their terrifying reputation? Behind their shadowy silence lies a world of astonishing phenomena, whispering quantum paradoxes, space-time warps, and even clues to the birth of the universe itself. Today, we're venturing beyond the textbook basics to uncover 30 jaw-dropping truths about black holes, facts so strange, they'll make you question everything you thought you knew. From the way they sing to how they might just be portals to other dimensions, these aren't your average astronomy lessons. This isn't just a journey through space, it's a plunge into the unknown, where every discovery feels like unraveling a piece of the universe's grandest riddle. So buckle up, by the time we're done, you'll see black holes not as celestial monsters, but as the universe's most enigmatic storytellers, holding tales of time, gravity, and perhaps even the fate of everything. Ready to step into the darkness? Let's begin. The first shocker about black holes: they're not holes at all. That name makes them sound like empty cosmic pits, but the reality is far stranger and far more extreme. Imagine crushing an entire star down into a space smaller than a city. That's essentially what a black hole is, an object so unimaginably dense, its gravity warps the fabric of spacetime itself. Picture Earth squeezed into the size of a marble. That's the kind of mind-bending compression we're talking about. What we call a black hole is really the aftermath of a catastrophic collapse where matter has been packed so tightly, it creates a gravitational grip nothing can escape. Pop culture loves painting them as cosmic vacuum cleaners, dark, empty tunnels sucking everything in. The truth, they're more like invisible mountains in space, so massive and compact that they bend light and time around them. Think of a bowling ball on a trampoline. The heavier the ball, the deeper the dent. A black hole is like that dent taken to the extreme, creating a pit so deep, anything that gets too close slides in with no way back. That point of no return, that's the event horizon, the famous edge of a black hole where even light becomes trapped. But here's where it gets wild. Black holes aren't just dead stars. Some, called supermassive black holes, lurk at the hearts of galaxies, weighing millions or even billions of times more than our sun. These giants didn't form from a single collapsing star. They grew over cosmic time, devouring gas, dust, and even other stars. Our own Milky Way has one named Sagittarius, a star, a silent titan around which our entire galaxy slowly spins. So no, black holes aren't holes. They're the universe's ultimate heavyweights, cosmic furnaces where the laws of physics as we know them start to break down. And believe it or not, this is just the tip of the gravitational iceberg. If you ever had the chance to hover near a black hole, you'd quickly discover one of the universe's most bizarre illusions. Time itself would start playing tricks on you. This isn't science fiction. It's a direct consequence of Einstein's theory of general relativity. The closer you get to a black hole's immense gravity, the slower time ticks compared to someone watching from a safe distance. Imagine an astronaut daring to approach the event horizon. From their perspective, seconds might feel normal, but back on Earth, years could be passing in the blink of an eye. Think of it like this: gravity doesn't just pull on objects, it stretches the very fabric of spacetime. A black hole's gravitational field is so intense that it creates what scientists call time dilation. Picture two clocks, one placed near a black hole, the other far away in empty space. the clock near the black hole would tick noticeably slower, as if it's moving through molasses. This effect has actually been measured here on Earth with ultra-precise atomic clocks. Even the slight difference in gravity between sea level and a mountaintop makes time run infinitesimally faster at higher altitudes. Near a black hole, though, the effect isn't subtle, it's extreme. Here's where it gets even stranger. If you could somehow hover right at the edge of a black hole's event horizon without falling in, time for you would nearly come to a standstill from an outsider's perspective. To a distant observer, you'd appear frozen, your movements stretched into an infinite slow motion. Meanwhile, you'd feel nothing unusual. Your watch would tick normally, your heartbeat steady. Yet the universe around you would seem to speed up, stars whipping across the sky as eons pass in moments. This isn't just theoretical. Astronomers have detected this time warping effect around supermassive black holes, where gas clouds orbit at dizzying speeds, their light stretched and redshifted by the immense gravitational pull. But what's truly mind-blowing, this time-bending phenomenon isn't confined to black holes. Every massive object, Earth, the Sun, even you, warps time to some degree. The difference is scale. A black hole cranks this effect up to 11, revealing just how elastic the universe's rules really are. So next time you glance at a clock, remember, time isn't the rigid, universal constant we assume it to be. Near a black hole, it's more like a river flowing at different speeds depending on where you stand, and in the deepest gravitational wells, it almost grinds to a halt. Black holes might seem like the silent monsters of the cosmos, but they're far from mute when they collide. They create ripples in spacetime so powerful, we can actually hear them. Not with our ears, of course, but through the marvel of gravitational wave detectors like LIGO and Virgo. Imagine two black holes spiraling toward each other, closer and closer, until they finally merge in a cataclysmic dance. The energy released sends shockwaves through the very fabric of the universe, stretching and squeezing spacetime itself. These vibrations travel across billions of light years, arriving at Earth as faint but detectable signals translated by scientists into eerie, otherworldly sounds. The first time researchers heard it, they called it a chirp, a rapid, rising tone that lasts less than a second. Played through speakers, it sounds like a distant bird call or a dropped coin spinning on a table. But this tiny sound carries unimaginable power. It's the echo of black holes weighing dozens of times more than our sun, smashing together at half the speed of light. That chirp is the universe's way of singing its most violent secrets to us. What makes these sounds so groundbreaking? For starters, they prove Einstein was right again. A century ago, he predicted gravitational waves as part of his theory of general relativity, but even he doubted we'd ever detect them. Then, in 2015, LIGO made history by capturing the chirp of two black holes merging 1.3 billion light-years away. It wasn't just confirmation of Einstein's genius, it opened an entirely new way to study the cosmos. Before gravitational waves, astronomers relied on light. Now they can listen to the universe, uncovering collisions and events invisible to telescopes. Here's the truly wild part. Each collision has its own acoustic signature. The pitch, the duration, even the volume of the chirp reveal details about the black holes involved. Their masses, their spins, how they orbited before merging. Some chirps are short and sharp, others warble like a drop of water. One famous example, detected in 2017, wasn't from black holes at all. It was the sound of two neutron stars colliding, a crash so bright it was seen in gamma rays, X-rays, and even visible light. That single event revolutionized astronomy, proving gravitational waves could guide us to cosmic treasure. So why does any of this matter? Because these sounds are more than just cosmic curiosities. They're clues to how galaxies form, how matter behaves under extreme conditions, and even how often black holes merge across the universe. Every chirp is like finding a new piece in a puzzle spanning billions of years. And with more detectors coming online like Japan's Kagra and India's planned LIGO India, the universe's soundtrack is only getting richer. Who knows what melodies are still out there waiting to be heard? One thing's certain, black holes might be invisible, but thanks to their gravitational songs, they're anything but silent. We've all seen how a spinning top warps the air around it, creating tiny whirlpools of motion. Now imagine that same principle, but scaled up to cosmic proportions. A black hole spinning so fast it drags the fabric of spacetime along with it. These aren't just hypothetical monsters, they're real, and they're called Kerr black holes, named after the physicist who first solved Einstein's equations for rotating black holes. Unlike their stationary counterparts, these cosmic whirlpools don't just sit there. They twist the universe around them like a spoon stirring honey. The numbers behind their spin are staggering. Some Kerr black holes rotate at nearly the speed of light, completing a full revolution in mere seconds. To put that in perspective, if Earth spun that fast, our planet's equator would be moving at over 1 billion miles per hour. That kind of rotational energy doesn't just bend space-time, it whips it into a frenzy, creating a region around the black hole called the ergosphere where nothing can stand still. Even light gets caught in this cosmic drag, forced to spiral along with the black hole's rotation. But how do we know any of this? Scientists have a clever way of measuring these invisible spins, X-rays. When a black hole feeds on nearby gas, that material doesn't just fall straight in, it forms a swirling disk, superheated to millions of degrees. As particles crash together, they emit X-rays, and the patterns in that radiation reveal the black hole's spin. Faster spins squeeze the inner edge of that disk closer to the event horizon, changing the X-ray signature in ways telescopes like NASA Chandra can detect. It's like reading cosmic fingerprints. Each twist and wobble in the light tells a story. One of the most extreme examples, the black hole at the center of galaxy NGC 1365. Observations suggest it's spinning at almost 90% the speed of light, warping spacetime so violently that it flings jets of particles thousands of light years into space. This isn't just a curiosity, it's a window into how black holes shape their galaxies. A rapidly spinning black hole can channel energy into those jets, heating surrounding gas and stunting star formation. In a way, these spinning giants act as cosmic regulators, controlling the growth of the galaxies they anchor. And here's the kicker. That spin might be the key to unlocking even wilder possibilities. Some theories suggest a spinning black hole could become a gateway, a natural wormhole stabilized by its own rotation. While that's still firmly in the realm of speculation, one thing's certain: Kerr black holes are proof that the universe doesn't just bend the rules. When it comes to gravity, sometimes it spins them into oblivion. Think black holes are only colossal, galaxy-swallowing behemoths. Think again. Hidden in the cosmos could be their tiny, elusive cousins, primordial black holes, some no larger than an atom but packing the mass of a mountain. These bizarre remnants might have formed in the first chaotic moments after the Big Bang, when the infant universe was so dense and turbulent that random pockets of matter collapsed under their own gravity. Unlike the black holes we know born from dying stars, these ancient relics could be floating among us right now, invisible and nearly undetectable. What makes them so fascinating? For one, they might solve one of astronomy's biggest puzzles, dark matter. Scientists know this mysterious substance makes up about 85% of the universe's mass, but it doesn't emit or reflect light, leaving no trace except its gravitational pull. Primordial black holes could be the missing piece. Imagine trillions of them scattered across galaxies like invisible cosmic pebbles, their combined gravity bending starlight and holding galaxies together. It's a tantalizing idea, one that turns these mini monsters from theoretical oddities into potential architects of the universe itself. So why haven't we found them yet? Detecting something so small and dark is like searching for a single grain of black sand in an endless desert. But scientists aren't giving up. Some hunt for telltale flashes when a primordial black hole passes in front of a distant star, briefly magnifying its light like a cosmic magnifying glass. Others listen for the faint pop of one evaporating, a phenomenon predicted by Stephen Hawking, where tiny black holes slowly leak radiation until they vanish in a burst of energy. There's even a chance they've left their mark right here on Earth. Some theories suggest these black holes could have slammed into our planet, leaving strange, unexplained seismic signals in their wake. The search is more than just cosmic curiosity. If primordial black holes exist, they'd rewrite our understanding of the universe's infancy, proving that the Big Bang wasn't just a smooth expansion but a violent, clumpy explosion where gravity ran wild. And if they are dark matter, that would mean the universe's greatest mystery isn't some exotic particle but black holes hiding in plain sight, tiny, ancient, and utterly transformative. The hunt continues, with every unturned stone in the cosmos holding the potential to upend everything we thought we knew. Here's something that might shatter every sci-fi movie you've ever seen: black holes don't actually suck. That's right, despite their terrifying reputation, these cosmic giants aren't galactic vacuum cleaners greedily pulling in everything around them. The truth is far more subtle and way more fascinating. A black hole's gravity works just like any other massive object, whether it's a star, a planet, or even your coffee cup. The difference: their gravitational grip becomes unbeatable once you cross a point of no return, the event horizon. Until then, matter can orbit a black hole just like planets orbit the sun, blissfully unaware of the danger lurking at the center. Think of it like a whirlpool in the ocean. If you're floating far away, the gentle currents might tug at you, but you're free to swim away. Get too close, though, and the swirling forces become impossible to resist. A black hole operates the same way. Stars, gas clouds, even light can dance around its edges for millions of years, tracing elegant ellipses until something nudges them just a fraction too close. That's when the real drama begins. This misconception matters because it changes how we picture black holes in action. Take the supermassive one at the Milky Way's heart, Sagittarius, a star. It's surrounded by a bustling crowd of stars, some skimming perilously near its event horizon. Yet they don't get sucked in. They're locked in stable orbits, some for longer than humans have existed. The only way they'd spiral inward is if something robbed them of energy, like friction from interstellar gas or a collision with another star. Even then, it's not the black hole actively pulling them down, it's physics playing out in slow motion. Here's where it gets even wilder. If you replaced our sun with a black hole of the same mass right now, Earth wouldn't get vacuumed into oblivion. Our planet would keep orbiting exactly as before, just in permanent darkness. The gravitational force at our distance wouldn't change, only the source would. That's the real mind bender. Black holes aren't magical gravity enhancers. They're just matter packed so densely that their escape velocity exceeds light speed. Anything outside their event horizon, it's business as usual for the laws of physics. So why does the sucking myth persist? Blame the way black holes feast. When they do pull in matter, usually gas from a doomed star, it doesn't just vanish quietly. The material forms a searing hot accretion disk, twisting and screaming as it's stretched by tidal forces. The resulting light shows can outshine entire galaxies, creating the illusion of an all-consuming monster. But peel back the spectacle and you'll find the same old gravity we've always known, just pushed to its most extreme edge. This isn't just semantics. Understanding how black holes truly interact with their surroundings helps explain why galaxies don't collapse into them, why some stars survive near misses, and how the universe balances on a knife's edge between chaos and order. The next time you hear someone describe a black hole as a cosmic vacuum, remember, the reality isn't about mindless destruction. It's a precise, elegant dance, one where gravity writes the rules and crossing the line changes everything. At the heart of our Milky Way, hidden behind swirling clouds of cosmic dust, sits a sleeping giant, Sagittarius, a star. This supermassive black hole weighs 4 million times more than our Sun, yet it's eerily quiet. Unlike the ravenous monsters at the centers of other galaxies, which devour matter and spew energy across the cosmos, our galactic anchor barely whispers. Scientists call this paradox the silent black hole problem, and unraveling it could rewrite what we know about how galaxies evolve. Take a look at Galaxy M87, home to one of the most active supermassive black holes ever observed. Its jet of superheated plasma stretches 5,000 light-years into space, a visible testament to its ferocious appetite. Then there's quasars, black holes so voracious they outshine entire galaxies as they rip apart stars and swallow gas clouds. Compared to these cosmic fireworks, Sagittarius, a star, seems almost lazy. Occasionally, it snags a passing gas cloud or star, letting out a faint X-ray burp before drifting back into dormancy. Why the stark difference? The answer might lie in its dining habits. Active black holes gorge themselves on steady streams of gas and dust, often because galactic collisions or turbulent orbits funnel material straight into their maws. But the Milky Way has been relatively peaceful for billions of years. With no recent galactic smash-ups to shake things up, Sagittarius, a star, is like a king without a banquet, left to nibble on the occasional interstellar scrap. There's another twist. Even when material does spiral toward our black hole, most of it gets slingshotted away by complex magnetic fields or settles into wide, stable orbits. Imagine throwing confetti near a fan. Some might get sucked in, but most just swirl around the edges. That's why only a trickle of matter actually reaches the event horizon, leaving Sagittarius, a star, on a perpetual cosmic diet. But don't mistake quiet for harmless. Infrared telescopes have caught glimpses of its temper flares bursting from its accretion disk, likely as trapped magnetic fields snap and reconnect. And in 2019, it briefly woke up, glowing 75 times brighter than usual for a few hours. Astronomers suspect a hapless asteroid or gas cloud strayed too close, becoming an unwitting snack. These flickers hint at dormant power, a reminder that our galactic center could one day roar to life. The silence might actually be a clue to something profound. Some theories suggest supermassive black holes cycle between active and quiet phases over billions of years, shaping their galaxies in the process. When active, their jets heat surrounding gas, stifling star birth. When quiet, like ours, stars form undisturbed. If true, Sagittarius, a star's calm isn't an anomaly. It's a phase in a grand celestial rhythm, one that's allowed our Milky Way to flourish with spirals of stars rather than fury. So while its stillness puzzles us, it might also be the reason we're here to ponder it at all. A quieter black hole means a stable galactic neighborhood, one where life has had the time and space to emerge. Next time you look at the night sky, remember, the darkness at the center of our galaxy isn't just empty. It's a silent guardian whose very hush may have written the story of our cosmic home. Black holes might be famous for trapping everything that crosses their event horizon, but they also have a breathtaking way of giving back, with jets of matter screaming into space at nearly the speed of light. These aren't just gentle cosmic breezes, they're colossal beams of energy stretching millions of light years across the universe, often outshining entire galaxies in their fury. Known as relativistic jets, they erupt from the poles of black holes, defying expectations by flinging material outward instead of swallowing it whole. How does a black hole, a gravitational prison, become a cosmic particle cannon? The answer lies in chaos and magnetic mayhem. When matter spirals toward a black hole, it doesn't just vanish quietly. Instead, it forms a searing hot disk of swirling gas and plasma, spinning faster and faster as it gets closer to the event horizon. Friction heats this disk to millions of degrees, creating a maelstrom of charged particles. But here's the twist: the black hole's rotation and its surrounding magnetic fields don't just feed the beast. They channel some of that energy into narrow, hyper-focused jets shooting straight up from its poles. These jets are cosmic engineering on an unimaginable scale. Picture a fire hose blasting water at near light speed, only instead of water, it's ionized particles, electrons, protons, and even heavier atomic nuclei accelerated to velocities so high they glow with intense radiation. Some of these jets stretch distances that dwarf their host galaxies, piercing through intergalactic space like celestial lighthouses, the most extreme example. The galaxy Messier 87, where a jet extending 5,000 light-years was famously captured by the Event Horizon Telescope, the same project that brought us the first image of a black hole's shadow. What fuels their incredible speed? It's a mix of raw power and precision. As particles spiral along twisted magnetic field lines, they're slingshotted outward, gaining energy like a roller coaster dropping from an impossible height. Some theories suggest the black hole's spin acts like a giant battery, transferring rotational energy directly into the jet. Others point to the insane pressures near the event horizon, where magnetic fields snap and reconnect, launching material like a cosmic catapult. Whatever the exact mechanism, the result is the same: nature's most powerful particle accelerators running on gravity's dime. And they're not just spectacular, they're galaxy shapers. These jets pump energy into their surroundings, heating interstellar gas and stifling star formation in their path. In some cases, they can even regulate the growth of galaxy clusters, pushing against the inflow of new material like a cosmic wind. Without them, the universe might look radically different, denser, hotter, and far more chaotic. So the next time you think of black holes as nothing but cosmic vacuum cleaners, remember, they're also celestial artists painting the universe with jets of fire that write the history of galaxies. And somewhere out there, right now, another jet might be forming, a beacon of destruction and creation, hurling matter across the cosmos at the speed of light. Stephen Hawking gave us one of the most startling truths about black holes: they aren't eternal. In fact, given enough time, they could completely evaporate, vanishing in a whisper of radiation. This phenomenon, known as Hawking radiation, upended everything scientists thought they knew about these gravitational giants. It turns out black holes aren't just cosmic dead ends. They're dynamic, slowly leaking energy back into the universe thanks to the bizarre rules of quantum mechanics. Here's how it works. Empty space isn't truly empty. It's a seething sea of virtual particles popping in and out of existence, thanks to quantum fluctuations. Normally, these particle pairs annihilate each other almost instantly, leaving no trace. But near a black hole's event horizon, something extraordinary happens. If one particle falls in while its partner escapes, the black hole loses a tiny bit of mass in the process. Over incomprehensibly long timescales, think trillions upon trillions of years, this slow leak adds up, causing the black hole to shrink until it finally winks out of existence. The implications are mind-bending. A stellar mass black hole might take longer than the current age of the universe to evaporate, but a tiny primordial one. It could be vanishing right now in a burst of gamma rays. Hawking's math even predicts that as a black hole shrinks, its evaporation speeds up, ending in a final, violent explosion. A cosmic firework with the energy of 1,000,000 nuclear bombs packed into a space smaller than an atom. This isn't just theoretical. While we've never directly observed Hawking radiation, its existence solves a paradox that haunted physicists for decades. If black holes swallow information irretrievably, it violates quantum mechanics' golden rule. Information can never be truly lost. Hawking radiation suggests that information isn't destroyed, it's encoded in the radiation, scrambled beyond recognition but still preserved in some form. What's truly wild is how this connects to the universe's ultimate fate. In a far, far future where all stars have burned out and galaxies have drifted apart, Hawking radiation might be the last flicker of activity, black holes glowing faintly as they dissolve into nothingness. It's a poetic twist. The universe's darkest objects could become its final light source, fading into the cold, quiet dark. Yet mysteries remain. Does the radiation really carry away information intact? Could we ever detect these faint quantum whispers? For now, Hawking's theory stands as a bridge between relativity and quantum mechanics, two fundamental theories that stubbornly refuse to fit together. And that's the real beauty of it. Black holes aren't just cosmic oddities. They're laboratories for testing the deepest laws of physics, proving that even the darkest corners of the universe have something to teach us. Imagine falling into a black hole, not to your doom, but into a tunnel through space and time, emerging in another universe entirely. This isn't just science fiction. It's a tantalizing possibility rooted in Einstein's own equations. The idea hinges on something called an Einstein-Rosen bridge, a theoretical shortcut through spacetime that could connect distant regions or even separate universes. At its heart, it suggests that black holes might not be cosmic dead ends, but portals to realms beyond our own. The math behind this is as elegant as it is mind-bending. When Einstein and physicist Nathan Rosen tackled the equations of general relativity, they found that black holes could, in theory, link to white holes, their hypothetical opposites. While a black hole's gravity is so strong nothing can escape, a white hole would repel everything, flinging matter outward like an unstoppable cosmic fountain. Connect the two with a bridge and suddenly you've got a wormhole, a tunnel where the entrance is a black hole, the exit a white hole, and the journey between them defies conventional notions of distance. But here's the catch: wormholes, if they exist, would be wildly unstable. The moment even a single particle tried to pass through, the tunnel would likely collapse faster than light could traverse it. To keep a wormhole open, you'd need something with negative energy, a mysterious form of matter that counteracts gravity. While quantum mechanics allows for fleeting negative energy fluctuations, sustaining enough to stabilize a wormhole remains firmly in the realm of speculation. That hasn't stopped scientists from dreaming. Some theories suggest that rotating black holes might naturally form traversable wormholes, their spin twisting spacetime into a stable passage. Others propose that advanced civilizations could engineer wormholes, threading them with exotic matter to create interstellar highways. For now, these ideas live on chalkboards and in supercomputer simulations, but they're more than just imaginative exercises. They're stress tests for our understanding of physics, probing whether the universe's rules might allow for such shortcuts. Science fiction loves this concept, from Interstellar's Gargantua to Stargate's iconic portals. Yet reality might be stranger. If wormholes exist, they could explain cosmic mysteries like why some particles seem to vanish or reappear under extreme conditions. They might even offer a loophole for time travel, with time dilation effects creating paths to the past or future. The truth, we don't know. Wormholes are mathematically possible, but nature has yet to show us one. Until then, black holes as gateways remain one of cosmology's most enchanting what-ifs, a reminder that the universe's deepest secrets might still be hiding in the darkest corners of spacetime. One of the most brilliant tricks astronomers use to spot invisible black holes, watching stars dance with ghosts. Across the cosmos, some stars don't travel alone. They're locked in a gravitational tango with an unseen partner, their paths warped by something massive, dark, and utterly mysterious. These binary systems, where a visible star orbits a hidden black hole, are nature's way of revealing cosmic secrets we'd otherwise never detect. Take Cygnus X1, the first black hole ever confirmed. Back in the 1960s, astronomers noticed something bizarre about this distant star system. Its X-ray emissions were off the charts. The visible star, a blue supergiant 30 times heavier than our Sun, seemed to be feeding material to an invisible companion. As gas spiraled from the star toward this dark object, it heated to millions of degrees, screaming its presence in X-rays. calculations showed the unseen partner had to be at least 15 solar masses crammed into a space smaller than a city. There was only one explanation: a black hole silently pulling its stellar partner through space. The discovery revolutionized astronomy. Before Cygnus X1, black holes were purely theoretical, mathematical curiosities in Einstein's equations. Suddenly, we had proof they were real, lurking in the darkness, just waiting to be unmasked by the stars they enslaved. Today, we've spotted dozens of these binary systems, each one a celestial detective story. The telltale signs: stars wobbling unpredictably, their light Doppler shifted as they're yanked by invisible gravity. Some, like the System Maxi J182+070, even flaunt their black hole's appetite, their stars flickering as they're slowly devoured, strip by strip. But here's the real kicker: these cosmic duos aren't just proof black holes exist. They're laboratories for studying gravity at its most extreme. In some systems, like the famous V404 Cygni, the black hole's pull is so strong it distorts its partner star into a teardrop shape, stretching it like taffy. In others, like GRS 1915+105, jets of plasma erupt from the black hole's poles, carving paths through interstellar space. Each system is a unique experiment, showing how matter behaves under forces we could never replicate on Earth. The strangest part: these black holes didn't start as monsters. They were once stars themselves, shining bright until their cores collapsed. Now they're cosmic phantoms, invisible yet undeniable, revealed only by the frantic orbits of the stars they refuse to let go. Every wobble, every X-ray flare, every distorted stellar scream is a message. The universe hides its darkest secrets in plain sight, if only we know how to look. If you ever had the misfortune of falling toward a black hole, you'd experience one of the universe's most bizarre and brutal phenomena: spaghettification. No, this isn't some cosmic pasta recipe. It's the horrifying process where tidal forces stretch you into a noodle-thin strand, atom by atom. The culprit: gravity's ruthless gradient, the simple fact that the pull on your feet would be exponentially stronger than the pull on your head if you were falling feet first. The difference in force would quickly turn you into human taffy, elongating your body into an unrecognizable filament long before you reach the event horizon. Picture this: as you approach the black hole, the gravitational tug on your lower half grows unbearable, yanking it downward faster than your upper body can follow. Muscles, bones, even individual cells would begin to separate under the strain, stretching like melted cheese in a cosmic fondue. Meanwhile, your sides would compress inward, squeezed by the same forces in a vice-like grip. The result: a grotesque human strand, thinner than a spaghetti noodle, hurtling toward oblivion. Even the toughest materials, steel, diamond, starship hulls, wouldn't stand a chance against these extreme tidal forces near a stellar mass black hole. But here's the twist: not all black holes spaghettify you the same way. The smaller the black hole, the more violent the stretching. A modest black hole with just a few solar masses would start ripping you apart thousands of miles from its event horizon, where the gravitational gradient is steeper. Fall toward a supermassive black hole like Sagittarius, a star, though, and you might cross the event horizon almost intact before the stretching begins. That's because their immense size spreads the tidal forces over a gentler curve, like dipping your toes into a lake versus plunging off a waterfall. This nightmare scenario isn't pure speculation. Astronomers have seen tidal disruption events, moments when stars stray too close to black holes and get shredded into glowing streams of plasma. In 2019, telescopes caught one such star being torn apart by a black hole 6 million times the Sun's mass, its debris forming a brilliant, twisting helix as it spiraled inward. The light from these events often outshines entire galaxies for months, a blazing testament to gravity's destructive power. Spaghettification isn't just morbid curiosity, it's a window into how matter behaves under the most extreme conditions. Each stretch and snap reveals secrets about black hole structure, the nature of gravity, and the limits of physical endurance. So while we'll never send a volunteer to test this firsthand, the universe has its own gruesome experiments underway, proving that in the shadow of a black hole, even the laws of anatomy get bent beyond recognition. We think of supermassive black holes as the universe's heavyweight champions until you meet their colossal cousins, the ultramassive black holes. These are the true titans of the cosmos, dwarfing even the supermassive black holes at galaxy centers. Take TUN 618, one of the most massive black holes ever detected. Clocking in at 66 billion times the mass of our Sun, this behemoth is so vast, it makes our entire solar system look like a speck of dust by comparison. To grasp just how absurdly large that is, picture the Sun as a grain of sand. On that scale, TUN 618 would be the size of a mountain range stretching from Earth's surface all the way into the upper atmosphere. Its event horizon, the point of no return, spans a diameter larger than our entire solar system, engulfing Pluto's orbit and beyond. If you swapped our Sun with this monster, its gravitational reach would extend past the Kuiper belt, pulling in planets, comets, and even distant asteroids like a cosmic whirlpool. But here's what really boggles the mind. We don't fully understand how these ultramassive black holes got so big. Supermassive black holes grow by merging with others or feasting on gas over billions of years, but TUN 618's size suggests it started gorging very early in cosmic history. Some theories propose these monsters were born from direct collapse black holes, primordial giants that formed when vast clouds of gas collapsed in the universe's infancy, skipping the star stage entirely. Others think they're the result of cosmic gluttony, merging with countless other black holes during countless galaxy collisions. Their sheer scale warps physics in surreal ways. For one, their event horizons are so vast, you could cross them without immediately noticing no dramatic spaghettification. And their gravity wells are so deep, they bend light into mesmerizing arcs, creating Einstein rings visible across billions of light years. Yet TUN 618 isn't alone. Black holes like Phoenix A and S50014 plus 81 rival its mass, each one a gravitational anchor for galaxies we can barely fathom. They're proof that the universe doesn't just break records, it annihilates them, crafting monsters so immense they redefine what we thought was possible. At the far edges of the observable universe, blazing brighter than a trillion suns, quasars stab through the cosmic dark like celestial lighthouses. These aren't just distant points of light. They're the most luminous objects in existence, powered by supermassive black holes in a feeding frenzy. A single quasar can outshine its entire host galaxy by 1,000 times, its brilliance fueled by the raw gravitational energy of matter screaming toward oblivion. But what makes these cosmic blowtorches even more astonishing is their ability to shape the very galaxies they inhabit, turning black holes from silent destroyers into architects of galactic destiny. Picture a supermassive black hole at the center of a young galaxy, surrounded by a vast sea of gas and dust. As material spirals inward, friction heats it to millions of degrees, creating an accretion disk so energetic it glows across the electromagnetic spectrum, X-rays, ultraviolet, visible light. But that's just the start. Some of this infalling matter gets funneled into jets erupting from the black hole's poles, accelerated to nearly light speed by twisted magnetic fields. The result, a quasar. Its light can travel billions of years to reach us, carrying snapshots of the universe's violent adolescence. The power output is almost incomprehensible. The brightest known quasar, S50014 plus 81, radiates as much energy every second as our Sun will over 30,000 years. That's not just a flashy spectacle, it's a galactic-scale power plant. But here's the twist, quasars don't just burn hot and fade, they shape their surroundings with ruthless efficiency. Radiation and particle jets blast outward, heating interstellar gas and stifling star formation like a cosmic wind scattering seeds. In some cases, they can even blow entire galaxies clean of star-forming material, leaving behind red and dead ellipticals where new stars rarely ignite. Yet this destruction has a creative side. Quasar winds can compress gas clouds at the edges of galaxies, triggering bursts of star formation in their wake. It's a cosmic feedback loop, black holes gorging on gas, then recycling the energy into sculpting their galactic homes. Some theories suggest quasars might even help regulate galaxy growth, preventing runaway expansion by shutting down their own fuel supply. The evidence: older galaxies often show a tight correlation between black hole mass and the size of their central star clusters, hinting at a deep co-evolutionary dance. But quasars aren't just relics of the past. In 2020, astronomers spotted one lurking in a relatively quiet modern galaxy, proving these engines can flicker back to life if fresh fuel arrives. Others, like the quasar S5003+024, flaunt double black holes at their cores, a chaotic tango of gravity that might explain their extreme luminosity. The lesson here is profound. Black holes aren't just endpoints for matter. They're cosmic catalysts, engines of creation and destruction woven into the fabric of galactic life. And quasars, they're the universe's way of reminding us that even in the darkest depths, there's light, violent, brilliant, and universe-shaping. Not every dying star gets the chance to become a black hole. In fact, most don't. Thanks to cosmic rules written in the laws of physics, the fate of a star depends on one critical factor: its mass, too small, and it fades quietly into a dense ember. Too massive, and it collapses into the universe's ultimate gravitational trap. But somewhere in between, stars meet far stranger fates, crushed into neutron stars or frozen as white dwarfs, their remains defying imagination. Take a star like our Sun. When it exhausts its nuclear fuel billions of years from now, it won't have the weight to trigger a dramatic collapse. Instead, it'll gently shed its outer layers, leaving behind a glowing core, a white dwarf. Packing about the mass of the Sun into a sphere the size of Earth, these stellar remnants are so dense that a single teaspoon of their material would weigh as much as an elephant. Yet they're cosmic lightweights compared to what comes next. The line between a white dwarf and something more exotic hinges on the Chandrasekhar limit, a critical threshold discovered by astrophysicist Subrahmanyan Chandrasekhar in the 1930s. This universal rule states that if a white dwarf's mass stays below 1.4 times that of our Sun, electron degeneracy pressure, a quantum force pushing against gravity will keep it stable. But cross that limit, and the star's own gravity overwhelms this pressure, triggering a catastrophic collapse. That's where neutron stars enter the picture. When a star between roughly 8 and 20 solar masses dies, it doesn't fade quietly. Its core implodes with such violence that protons and electrons fuse into neutrons, creating a city-sized ball of pure nuclear matter. A sugar cube-sized chunk of this exotic material would outweigh Mount Everest, but even neutron stars have their limits, pushed past about 2.2 solar masses, and not even neutron degeneracy pressure can resist gravity's pull. The core keeps collapsing, crushing down further until spacetime itself warps into a black hole. The exceptions are as fascinating as the rules. Some white dwarfs cheat death by siphoning mass from a companion star, briefly flirting with the Chandrasekhar limit before exploding as supernova. Others, in binary systems, might collide and merge, catapulting themselves past the threshold in a single, fiery instant. Meanwhile, the heaviest neutron stars teeter on the edge of becoming black holes, their very existence probing the limits of matter's ability to resist gravity. These thresholds aren't just cosmic trivia, they're the universe's way of sorting its dead into categories. Too light, and you become a diamond in the dark. Too heavy, and you vanish into the abyss. but for those stars balanced on the knife's edge, death is anything but quiet. It's a metamorphosis into something far stranger. Black holes were long thought to be the ultimate baldies of the cosmos, so featureless they could be described with just three simple numbers: mass, spin, and charge. This elegant idea, known as the no-hair theorem, suggested that no matter how complex an object was before being swallowed, whether a star, a planet, or an entire spaceship, once it crossed the event horizon, all distinguishing details would be erased, leaving behind a perfectly smooth, information-less void. But like a detective noticing stray threads at a crime scene, physicists have begun questioning this clean-shaven picture. Recent studies hint that black holes might actually have hair, subtle, lingering imprints of what they've consumed, etched into their gravitational fields like cosmic fingerprints. The implications of hairy black holes are staggering. If true, it would mean these gravitational giants don't completely destroy information. They preserve traces of their meals in ways we're only beginning to understand. Picture a black hole devouring a star with a powerful magnetic field. According to classical physics, that magnetic signature should vanish without a trace. But newer models suggest the black hole's own gravitational field might retain faint hairs, distortions in spacetime that encode details about what fell in. These wouldn't be literal strands, of course, but rather quantum or gravitational markers clinging stubbornly to the event horizon, whispering secrets about the black hole's past. This debate isn't just academic, it cuts to the heart of one of physics' biggest paradoxes, the black hole information problem. Quantum mechanics insists information can never be truly destroyed, yet the no-hair theorem seemed to violate that principle by erasing all record of infalling matter. Hawking radiation offered a partial solution, suggesting information might leak out via quantum particles. But the hair hypothesis takes it further, proposing that black holes aren't the cosmic shredders we thought. Instead, they might be meticulous archivists preserving data in their gravitational swirls. Evidence is still tentative but tantalizing. Simulations of collapsing stars show that certain properties like magnetic fields or quantum vibrations could imprint themselves on a black hole's external geometry. Other studies explore how soft hairs, infinitesimal spacetime ripples near the horizon, might store data like a celestial hard drive. Even gravitational wave detectors might soon join the hunt, searching for anomalies in black hole mergers that betray hidden structures. For now, the no-hair theorem remains the leading model, but the cracks are showing. If black holes truly have hair, it wouldn't just rewrite textbooks. It would redefine our understanding of how the universe preserves its history, proving that even the darkest voids leave clues behind. And somewhere out there, a black hole's gravitational strands might be trembling with stories, waiting for us to learn how to listen. Most supermassive black holes grew gradually over billions of years, but what if some were born giant? This startling possibility leads us to one of cosmology's most intriguing mysteries: direct collapse black holes. Unlike typical black holes formed from dying stars, these primordial behemoths may have materialized fully grown in the universe's chaotic infancy, emerging from collapsing gas clouds so massive they skip the star stage entirely. Picture vast cosmic nurseries in the early universe, where clouds of pristine hydrogen and helium, untouched by heavier elements, collapsed under their own weight. Without dust or metals to help them cool and fragment into stars, these clouds could have imploded directly into black holes with masses tens of thousands of times our sun's stellar titans, appearing almost overnight in cosmic terms. The math behind this is compelling. In today's universe, gas clouds fragment too easily to form direct collapse black holes. Their material splits into countless stars instead. But in the first 100 million years after the Big Bang, conditions were radically different. Intense ultraviolet light from early galaxies may have prevented molecular hydrogen from cooling certain gas clouds, keeping them hot and monolithic. Without this cooling mechanism, nothing could stop these mega clouds from crumpling into gravitational singularities. Simulations show it would happen in a cosmic blink, a cloud hundreds of light years across pancaking into a black hole large enough to anchor an entire future galaxy. Why does this matter? Because these primordial giants could explain an astronomical headache: how supermassive black holes appeared so early. Quasars powered by billion solar mass black holes have been spotted just 700 million years after the Big Bang, too soon for conventional growth models. A direct collapse seed would solve this by giving black holes a colossal head start. Rather than growing slowly from stellar remnants, they'd begin life as heavyweight contenders, swallowing gas and merging with others to become today's galactic centerpieces. The black hole at our Milky Way's heart might trace its lineage to one of these ancient monsters. The hunt for evidence is on. Astronomers scrutinize distant quasars for chemical fingerprints hinting at rapid early growth. Others search for intermediate mass black holes, potential missing links between direct collapse seeds and supermassive giants. Even gravitational wave detectors might one day catch echoes of mergers between these primordial titans. If confirmed, direct collapse black holes wouldn't just rewrite cosmic history, they'd reveal how the universe built its gravitational scaffolding before the first stars finished shining. The cosmos isn't just a silent void, it's alive with vibrations, and some of the most violent events send shockwaves rippling through spacetime itself. When two black holes spiral toward each other in a gravitational death spiral, their collision doesn't just vanish into darkness. Instead, it sends out waves of distortion, gravitational waves that stretch and squeeze the fabric of the universe. These ripples travel at the speed of light, carrying echoes of the most energetic events since the Big Bang. And in 2015, humanity finally learned how to listen. That year, the Laser Interferometer Gravitational Wave Observatory, LIGO, caught the faintest whisper from a pair of black holes 1.3 billion light-years away. The signal lasted just 0.2 seconds, but it was unmistakable. The rapid chirp of two black holes, one 29 times the Sun's mass, the other 36, merging into a single 62 solar mass monster. In that instant, 3 suns worth of pure energy transformed into gravitational waves, warping spacetime so powerfully that the distortion reached Earth, though by then, it had weakened to 1,000th the width of a proton. The discovery didn't just confirm Einstein's century-old prediction, it shattered expectations. Before LIGO, astronomers assumed most black hole pairs would be roughly equal in mass. Instead, they found mergers with wildly mismatched partners, like the 19 and 7 solar mass black holes that combined in 2019. Some collisions produce mind-bending spins, like GW 190514, where one black hole twirled so fast it nearly tipped over mid-merger. Others defy explanation entirely, like GW 190521, a collision so massive its remnants shouldn't exist under current models. What makes these mergers truly revolutionary is how they've exposed the universe's hidden demographics. Before gravitational waves, stellar mass black holes were nearly invisible. Now, we know they're far more common than imagined. LIGO and its European counterpart, Virgo, have detected over 90 mergers since 2015, revealing a cosmic menagerie. Black holes orbiting neutron stars, pairs locked in tight orbits, even potential hierarchical mergers where one black hole is itself the product of an earlier collision. The technology behind these detections is as astonishing as the discoveries. LIGO twin observatories, one in Louisiana, the other in Washington, use lasers traveling down 2.5 mile long vacuum tubes to measure infinitesimal spacetime distortions. When a gravitational wave passes, one arm lengthens while the other contracts, shifting the laser's interference pattern by less than 1/10,000th the width of a proton. It's like measuring the distance to Alpha Centauri, 4.37 light-years away with an accuracy of one human hair's width. Yet the real treasure lies in what these waves reveal about black holes' birthplaces. Some merging pairs likely formed from binary stars that collapsed in tandem. Others might have met in dense stellar environments like globular clusters, where gravitational encounters shoved them together. The most massive mergers hint at exotic origins, perhaps primordial black holes from the universe's first moments, or remnants of stars that formed before heavy elements existed. Every chirp is a Rosetta Stone for decoding gravity's extremes. When black holes merge their final moments before collision, the ring down probes spacetime's very nature. The resulting vibrations, like a struck bell's reverberations, test whether black holes truly obey Einstein's predictions or hide quantum secrets. Already, deviations from theory have physicists questioning if event horizons behave as we thought, or if exotic physics like supersymmetry might lurk in these violent encounters. As detectors grow more sensitive, with upgrades like LIGO India and space-based observatories like LISA on the horizon, the universe's soundtrack will only grow richer. Somewhere out there, another pair of black holes is spiraling toward collision, their dance destined to send tremors through spacetime. And when those waves finally reach us, they'll carry answers to questions we haven't even learned to ask yet. Just beyond the event horizon of a black hole lies one of the most mesmerizing regions in the universe, a place where light itself becomes trapped in an endless cosmic dance. This boundary, known as the photon sphere, is a razor-thin zone where gravity bends spacetime so severely that photons, particles of light, are forced into perfect circular orbits. Picture a cosmic carousel with no exit. Light enters this orbit and, unless disturbed, will loop around the black hole forever, neither plunging inward nor escaping into space. It's a gravitational hall of mirrors where the universe's fastest traveler becomes a prisoner of pure geometry. The photon sphere isn't just a theoretical oddity, it's the key to the black hole's haunting silhouette. When the Event Horizon Telescope captured the first image of a black hole in 2019, that iconic dark shadow surrounded by a fiery ring, that glow comes from light skimming the photon sphere, bent so sharply by gravity that it arcs around the void and back toward our telescopes. Imagine standing near this boundary, holding a flashlight. Point it sideways and the beam would curve tightly around the black hole, potentially hitting you in the back after completing a full loop. The closer you get to the photon sphere, the more times light can circle the black hole before either escaping or vanishing inward, creating a multi-layered halo effect in images. But here's the catch: these orbits are catastrophically unstable. The slightest perturbation, a passing dust grain or a ripple in spacetime, can knock photons out of their perfect loops, either hurling them into oblivion or flinging them outward to be seen by distant observers. That's why the photon sphere isn't a solid shell of trapped light, but a fleeting, chaotic region where photons jostle like marbles balancing on the edge of a bowl. Some slip free, becoming the bright ring we observe. Others spiral inward, adding to the black hole's darkness. This delicate balance has stunning observational consequences. When astronomers study black holes, the photon sphere's radius, about 1.5 times the event horizon size, serves as a cosmic ruler. By measuring the apparent size of a black hole's shadow, they can calculate its mass and spin with unprecedented precision. The photon ring's thickness and brightness even encode secrets about the black hole's turbulent surroundings, like the frenzy of its accretion disk or the strength of magnetic fields nearby. Yet the photon sphere isn't unique to black holes. In theory, any sufficiently dense object could create one. If you crushed Earth into a pea-sized nugget, light could orbit it too. But only black holes warp spacetime enough to make this phenomenon visible across cosmic distances. And it's not just light that gets caught in this gravitational ballet. Gravitational waves, ripples in spacetime itself, can also orbit in a similar zone, creating echo-like signatures that future detectors might uncover. the photon sphere is more than a cosmic curiosity. It's a stark reminder that near a black hole, even the universe's strictest rules, like light's unwavering speed, bow to gravity's will. Here, photons don't travel in straight lines but in celestial pirouettes, painting the darkness with rings of trapped brilliance. And every time we glimpse that glowing halo in telescope images, we're seeing the universe's most extreme physics etched in light, a perfect circle of fire, scribed by gravity's relentless hand. Stephen Hawking's most revolutionary idea wasn't about how black holes live, it was about how they die. These gravitational giants, long thought to be eternal prisons for matter and energy, might actually fade away over time, dissolving into faint whispers of radiation. The process, now known as Hawking radiation, suggests that black holes aren't permanent fixtures of the cosmos. They're more like cosmic ice cubes, slowly evaporating in the dark until nothing remains. But here's the catch: their lifespans are so staggeringly long, they make the age of the universe seem like a fleeting moment. To understand how this works, we have to peer into the quantum froth at the very edge of a black hole's event horizon. According to quantum mechanics, empty space isn't truly empty, it's a seething sea of virtual particles popping in and out of existence. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But when this happens near a black hole, gravity can yank one particle across the event horizon while its partner escapes into space. The fleeing particle carries energy away, and since energy can't be created from nothing, the black hole loses mass to balance the equation. Over time, this slow leak adds up, causing the black hole to shrink and eventually vanish. Now, let's talk timescales. A typical stellar mass black hole, say 10 times the mass of our Sun, would take around 10 to the power of 67 years to fully evaporate. That's a 1 followed by 67 zeros, a number so large, it dwarfs the current age of the universe, a mere 13.8 billion years, by unimaginable orders of magnitude. Even a modest black hole would outlast every star in the cosmos, lingering long after galaxies have burned out and space itself has stretched into cold, silent darkness. But here's the twist: the smaller a black hole gets, the faster it evaporates. In its final moments, it would unleash a burst of energy equivalent to millions of nuclear bombs, a fleeting spark in the void. This isn't just theoretical, it reshapes how we think about the universe's ultimate fate. In the far, far future, long after the last stars have flickered out, black holes might be the only structures left. And as they slowly decay, they could become the last sources of light and heat in an otherwise cold, empty cosmos. It's a poetic irony. The universe's darkest objects might one day be its final beacons, flickering out one by one until even they are gone. Hawking's discovery also cracked open one of physics' toughest paradoxes, the black hole information problem. If black holes evaporate completely, what happens to all the information they swallowed? Quantum mechanics insists that information can never be truly lost. Hawking initially thought it vanished forever, but later theories suggest the radiation itself might be subtly encoded with the secrets of everything that fell in. Like a cosmic hologram, the surface of the event horizon could preserve data in scrambled form, slowly leaking it back into the universe as the black hole fades. So while we'll never witness a black hole's death firsthand, their theoretical evaporation forces us to reconsider the most fundamental laws of reality. It's a reminder that even the mightiest structures in the cosmos are bound by time, and that nothing, not even a black hole, lasts forever. When two black holes collide and merge, the resulting cosmic behemoth doesn't just settle down quietly, it rings like a colossal bell, sending gravitational vibrations echoing through spacetime. These aren't subtle tremors. The newborn black hole convulses violently, shedding distortions in waves that ripple across the universe at light speed. Scientists call this phenomenon ring down, the final, fading oscillations of a black hole settling into its new form. It's as if the universe itself strikes a gong and the sound is written in the fabric of reality. These vibrations are far more than cosmic noise. They're a goldmine of information about the black hole's structure. Just as you can tell whether a bell is made of brass or silver by its ring, physicists can decode the frequency and decay of these gravitational waves to reveal the black hole's mass, spin, and even the shape of its event horizon. The numbers are staggering. A typical post-merger black hole might vibrate at frequencies of hundreds of cycles per second, distorting spacetime so profoundly that detectors like LIGO can pick up the signals billions of light years away. The physics behind this wobble is surprisingly elegant. Imagine tossing a pebble into a pond. The ripples start out large and chaotic, then gradually smooth into smaller, orderly waves. A merged black hole behaves similarly. Right after collision, it's misshapen, like a lumpy ball spinning wildly. As it radiates gravitational waves, it loses energy, smoothing out until it becomes a perfect sphere or a slightly flattened spheroid, depending on its rotation. The tones of these waves follow precise mathematical patterns predicted by Einstein's equations, acting as fingerprints for the black hole's properties. One of the most startling discoveries came from the first gravitational wave detection in 2015. The signal GW150914 didn't just capture the black hole's inward spiral, it recorded their ring-down too. By analyzing the wobbles, scientists confirmed the final black hole weighed 62 solar masses and was spinning at nearly 2/3 the speed of light. Even more remarkably, the vibrations matched Einstein's predictions with near-perfect accuracy, proving that black holes really do behave like the smooth, simple objects described by general relativity. But not all ring-downs are textbook perfect. Some mergers produce black holes that vibrate in unexpected ways, hinting at exotic physics lurking beyond Einstein's theory. For instance, if event horizons aren't perfectly smooth, if they have hairs or quantum fuzz, their ring-down signatures might carry subtle anomalies. Future detectors, like the space-based LISA Observatory, could spot these deviations, potentially uncovering cracks in our current understanding of gravity. These wobbling black holes also offer clues about extreme environments we can't otherwise probe. The frequencies of their vibrations depend on the black hole's internal structure, which remains one of cosmology's deepest mysteries. Does all infalling matter get crushed into a singularity, or is there some exotic state of matter at the core? Ring-downs might hold the answer, acting as cosmic sonar mapping the invisible depths. Every merger is a symphony of space-time with black holes as the instruments. And as our detectors grow more sensitive, we're not just hearing the loudest crashes, we're tuning into the whispers, the faint after-echoes of collisions that shaped the universe eons ago. Each wobble, each ripple, is a note in gravity's grand composition, revealing secrets written in the language of warped space-time. You've probably heard the nightmare scenario. The moment you cross a black hole's event horizon, your body gets shredded by tidal forces. But here's a twist that flips the script. Depending on the black hole's size, you might actually survive the crossing. That's right, plunge into a supermassive black hole, and you could, in theory, sail right through the event horizon without even realizing it. The key lies in gravity's hidden gradient, a subtle detail that separates cosmic butchers from surprisingly gentle giants. Tidal forces. The difference in gravity's pull from your head to your toes are what make black holes lethal. Near a small, stellar mass black hole, this gradient is extreme. The pull on your feet could be exponentially stronger than on your head, stretching you into spaghetti before you even reach the event horizon. But supermassive black holes, like Sagittarius, a star at the Milky Way center, are a different beast. Their event horizons are so vast, millions of kilometers across, that the gravitational gradient is shallow. Fall into one, and the tidal forces near the horizon might be no worse than the tug you'd feel stepping into a warm bath. You'd cross the point of no return completely intact, blissfully unaware of the abyss you've just entered. This isn't just speculation, it's baked into the math. The tidal force at the event horizon scales inversely with the square of the black hole's mass. Translation: double the black hole's size and the spaghettifying force drops by a factor of 4. A black hole with millions of solar masses could have tidal forces gentle enough for a human to withstand, at least until venturing deeper toward the singularity. But don't pack your interstellar suitcase just yet. Surviving the horizon is one thing, escaping the black hole's grip is impossible. Once you're inside, every path forward in time, sideways in space, leads inexorably toward the singularity. There's no backtracking, no last-minute rescue. The real danger isn't the horizon itself, but the inescapable doom waiting deeper in. And here's the cruel irony. While you'd feel nothing unusual at the moment of crossing, observers outside would see your plunge frozen in time, your image redshifted into oblivion as gravity distorts the light you emit. The debate gets even wilder when quantum mechanics enters the mix. Some theories suggest the event horizon might not be the smooth, mathematical boundary relativity predicts, but a seething firewall of high-energy particles, a literal wall of destruction. Others argue that quantum effects could subtly alter the horizon's nature, making it a less lethal threshold. For now, these ideas remain untested, leaving the question open: is the event horizon a silent gateway or a violent cosmic shredder? One thing's certain: if you ever find yourself drifting toward a supermassive black hole, you'll have a brief window of awe before the inevitable. The sky ahead would warp into a shrinking circle of light, stars bending into bizarre rings as gravity lenses their light. Behind you, the universe would appear to speed up, its final flashes of light blue-shifting into gamma rays before darkness swallows everything. It's a one-way trip into the unknown, where the laws of physics as we know them cease to apply. So could you survive crossing the event horizon? Theoretically, yes, if the black hole is big enough. But survival here is a fleeting gift, a momentary reprieve before the universe's most extreme physics takes over. It's a reminder that black holes aren't just death traps, they're the ultimate test of our understanding of reality, where even the simplest questions lead to the edge of human knowledge. What if the answer to one of astronomy's greatest mysteries has been hiding in plain sight, cloaked in the very darkness it creates? For decades, scientists have struggled to explain dark matter, the invisible substance making up 85% of the universe's mass. It doesn't emit, reflect, or absorb light, revealing itself only through gravitational tugs on galaxies and starlight. But here's a radical idea: dark matter might not be an exotic particle at all. It could be countless primordial black holes, forged in the universe's violent infancy and drifting unseen through the cosmos like ghostly remnants of creation. The theory isn't as far-fetched as it sounds. Primordial black holes wouldn't form from collapsing stars like their modern counterparts. Instead, they'd be relics of the Big Bang's chaotic first seconds, when density fluctuations in the searing hot young universe could have collapsed directly into black holes. Some might weigh as little as asteroids, others as much as stars, all lurking undetected for billions of years. Their sheer numbers could explain dark matter's gravitational effects without invoking undiscovered particles. Imagine trillions of these invisible specks scattered throughout galaxies, their combined mass bending light and shaping cosmic structures exactly as dark matter does. Evidence for this idea has flickered in and out of focus for decades. In the 1970s, physicist Stephen Hawking calculated that small primordial black holes could still survive today, peppering the cosmos. More recently, gravitational microlensing surveys where telescopes watch for brief brightening of stars caused by unseen objects passing in front have hinted at a population of compact dark objects. Some events match the expected signature of black holes between asteroid and moon masses, drifting invisibly through the Milky Way. Even more provocative are the gravitational wave detections of surprisingly heavy black hole mergers, which some theorists argue could be primordial in origin. But the theory faces glaring challenges. If primordial black holes were abundant enough to account for all dark matter, we'd expect to see more microlensing events than observed. The survival of delicate early universe structures like dwarf galaxies also poses problems. Too many small black holes would have disrupted them. And there's the puzzle of their formation. Conditions in the early universe had to be just right to spawn primordial black holes without overproducing them. Too many and the cosmos would look radically different. Too few and they can't explain dark matter's dominance. The debate splits astrophysics into passionate camps. Critics point to the lack of definitive microlensing signals and the elegance of particle-based dark matter theories. Supporters counter that primordial black holes are elegantly minimal, no new physics required beyond Einstein and Hawking. Some propose a hybrid solution. Maybe dark matter is mostly particles, with primordial black holes making up a fraction. Others speculate that these ancient black holes could be hiding in the cores of neutron stars, their presence betrayed by subtle heating or gravitational waves. What's at stake isn't just academic. If primordial black holes are dark matter, it would rewrite cosmic history, suggesting the early universe was far lumpier and more violent than we thought. It could also solve lingering mysteries, like why some black holes merged so soon after the Big Bang, or why supermassive black holes appeared in galaxies shockingly early. The implications ripple outward. These black holes might have seeded galaxy formation, their gravity providing the scaffolding for stars to assemble. For now, the hunt continues. New telescopes scanning for microlensing, gravitational wave detectors catching faint merger echoes, even quantum experiments probing for subtle gravitational effects, all could tip the scales. Whether primordial black holes are dark matter's architects or just cosmic red herrings, their story is entwined with the universe's deepest secrets. And somewhere out there, in the vast dark between stars, the answer might be lurking not as an exotic particle, but as a whisper from the dawn of time itself. Black holes are legendary for their violent appetites, but even the most voracious cosmic predators sometimes bite off more than they can chew. Take the bizarre case of SS433, a black hole locked in a gravitational tango with a companion star, where the black hole's own relativistic jets, usually flung far into space, curve backward like cosmic boomerangs and plunge right back into the monster that created them. This isn't just a fluke, it's a full-blown astrophysical paradox challenging everything astronomers thought they knew about how black holes interact with their most powerful outbursts. Normally, jets erupt from a black hole's poles at nearly light speed, streaming outward in razor-straight lines for thousands of light years. But SS433's jets behave like nothing else in the known universe. Instead of racing away, they twist into tight corkscrews, dragged down by the black hole's gravity until they loop back toward the event horizon in a stunning act of self-cannibalism. Imagine a fire hose blasting water upward, only for the stream to arc backward and disappear down the drain. It defies intuition. The culprit, a combination of insane physics and gravitational sleight of hand. SS433's black hole isn't just eating, it's dining with reckless abandon, gulping down so much gas from its companion star that the sheer volume of material overwhelms the jets. As matter spirals inward at breakneck speeds, it creates a swirling maelstrom of magnetic fields and turbulence, warping the jet's trajectory. At the same time, the black hole's spin acts like a cosmic mixer, churning spacetime itself into a vortex that bends the jets inward. It's a gravitational tug-of-war where the black hole's appetite ultimately wins, pulling its own fireworks show back into the darkness. What makes this discovery so revolutionary isn't just the spectacle, it's the implications. For decades, astronomers assumed jets were a one-way ticket out of a black hole's grasp, carrying energy and matter far into intergalactic space. But if even a fraction of that energy can boomerang back, it changes how we model black hole feedback, the process by which these monsters regulate star formation and galaxy growth. In SS433's case, the returning jets inject chaos into the accretion disk, creating shockwaves that heat surrounding gas and potentially stifle the black hole's own feeding frenzy. It's a self-regulating loop of cosmic gluttony and consequences. The real puzzle is how common this phenomenon might be. SS433 is extreme, yes, but it's not alone. Recent observations of other microquasars, like GRS 1915+105, show hints of similar jet bending. Even some supermassive black holes might be quietly recycling their own outflows, hiding the evidence in subtle X-ray flickers or distorted radio emissions. If this behavior is widespread, it could rewrite the playbook on how black holes influence their galactic neighborhoods, turning them from simple destroyers into complex cosmic recyclers. Here's the kicker: this discovery wouldn't have been possible without a stroke of cosmic luck. SS433's jets are tilted just right from Earth's perspective, letting astronomers track their full twisted path. Had they been pointing straight at us or away, the spiral structure would have been invisible, lost in the glare. It's a humbling reminder that for all their power, black holes still keep their most astonishing secrets hidden in plain sight, waiting for the perfect alignment and the perfect moment to reveal them. At the very core of a black hole, where gravity's grip becomes infinite and spacetime stretches beyond comprehension, lies the most enigmatic prediction in all of physics, the singularity. According to Einstein's equations of general relativity, all the matter a black hole has ever consumed gets crushed into a single, dimensionless point of infinite density, a place where the laws of physics as we know them cease to function. No volume, no structure, just pure, unfathomable extremity. It's as if the universe has drawn a mathematical line in the cosmic sand and written, "Here reality ends." But infinity isn't just a number, it's a red flag. When equations spit out infinite values, it's usually a sign that our understanding is incomplete. Think of it like a calculator dividing by zero. The machine freaks out because the operation defies logic. The singularity does the same to physics. It's where relativity, which governs the very large, collides head-on with quantum mechanics, the rules of the very small. One predicts a point of infinite curvature, the other insists that nature abhors infinities. Something's got to give. This clash isn't just academic, it's a crisis hiding in plain sight. If singularities truly exist, they're cosmic censorship in action, hiding their impossible physics behind event horizons. But peel back that curtain, and you're left with questions that shake the foundations of science. What happens to information trapped in a singularity? Does time truly stop there, as equations suggest, or is the singularity just a placeholder, a glaring signpost that we're missing a deeper theory, one that unifies gravity and quantum mechanics into a single framework? Enter the contenders. String theory proposes that singularities might be replaced by fuzzy, vibrating strings or higher dimensional brains. Loop quantum gravity suggests spacetime itself could be granular at the tiniest scales, preventing infinite density. Even wilder ideas like holographic duality imply the singularity isn't a place at all, just a shadow of quantum processes playing out on the event horizon surface. Each theory dances around the same truth: infinity is probably an illusion, a mathematical artifact of our incomplete knowledge. The irony is thick. Black holes, born from the death of stars, might hold the keys to the universe's deepest secrets. To crack the singularity's code, we'd need a theory of quantum gravity, a Rosetta Stone to translate between relativity's warped spacetime and quantum mechanics' probabilistic weirdness. Until then, the singularity remains the ultimate cosmic cliffhanger, a mathematical paradox lurking in the dark, waiting for someone to rewrite the rules. Black holes don't just warp space, they bend it into cosmic magnifying glasses, revealing corners of the universe we'd otherwise never see. This phenomenon, called gravitational lensing, turns these gravitational titans into nature's ultimate telescopes. When a black hole aligns perfectly between Earth and a distant light source like a galaxy or quasar, its immense gravity curves spacetime so dramatically that light from behind it gets bent around its edges, creating distorted, often ring-like images known as Einstein rings. These aren't just beautiful quirks of physics, they're powerful tools for probing everything from dark matter to the universe's expansion rate. One of the most stunning examples is the black hole in galaxy JVAS-B 1938+666. When astronomers trained radio telescopes on it, they didn't just see the black hole's shadow, they spotted a near-perfect halo of light from a galaxy 12 billion light-years behind it, warped into a glowing circle by the black hole's gravity. This Einstein ring, named for the theory that predicted it, acts like a cosmic zoom lens. The black hole's distortion amplifies the background galaxy's light, making faint structures visible that would otherwise be lost in the void. It's as if the universe handed scientists a free Hubble deep field image, courtesy of a black hole's gravitational grip. But the real magic lies in what these lenses reveal. Because the amount of bending depends on the black hole's mass, astronomers can literally weigh the lensing black hole by measuring the ring's size. In some cases, like the system MG 1654+1346, the lensed light reveals multiple images of the same background object, a cosmic hall of mirrors that lets researchers triangulate distances across the universe with unprecedented precision. These measurements have become critical for calculating the Hubble constant, the rate at which the cosmos expands, helping resolve tensions between different measurement techniques. Gravitational lensing also exposes the invisible. When the lensed light doesn't match predictions, it often hints at unseen mass, likely dark matter, altering the black hole's gravitational field. The black hole in cluster Abell 370, for instance, lenses background galaxies into streaks and arcs that reveal vast, invisible halos of dark matter weaving through the cluster. It's like watching wind bend trees to map an unseen storm, and sometimes the lenses themselves become the subject of discovery. The system SPT SJ0418-4759 stunned astronomers when its Einstein ring flickered unexpectedly, a sign that the background quasar wasn't just being lensed, but was also harboring a supermassive black hole with violent brightness swings. The black hole in front became a magnifier, the one behind a cosmic strobe light. This gravitational lensing isn't limited to supermassive black holes. Even stellar mass black holes, if they pass precisely in front of distant stars, can create microlensing events that betray their presence. Projects like OGLE and AMOE scan millions of stars nightly, hunting for these telltale brightenings, a way to sense hidden black holes drifting undetected through our galaxy. What's next? With telescopes like the Vera Rubin Observatory coming online, astronomers expect to find thousands more lensed systems, each one a snapshot of gravity's power to twist light into revelations. Black holes, it turns out, aren't just cosmic voids, they're the universe's way of sketching its own blueprint, using spacetime itself as the pen. And every Einstein ring, every warped galaxy, is a clue waiting to be decoded. Every black hole we've ever observed hides its singularity behind an event horizon, a point of no return that keeps the universe's most violent physics veiled from view. But what if some singularities exist without this cosmic curtain? Meet the most provocative rebels in theoretical astrophysics, naked singularities. These hypothetical monsters flaunt their infinite densities in plain sight, violating a cornerstone principle called cosmic censorship, the idea that nature abhors a bare singularity. The debate over their existence isn't just academic. It's a battle over whether the universe plays by self-imposed rules or occasionally throws caution to the wind. The concept of cosmic censorship was first proposed by physicist Roger Penrose in the 1960s as a kind of cosmic hygiene law. Without it, singularities could warp spacetime so unpredictably that cause and effect would break down, rendering physics impossible. Think of it like a cosmic quarantine event. Horizons act as containers, preventing the singularity's infinite weirdness from infecting the rest of the universe. Naked singularities, by contrast, would be like unshielded nuclear reactors, radiating paradoxes into space with no barrier to contain them. Yet despite Penrose's conviction that nature forbids such exposures, the math doesn't rule them out entirely. Certain extreme scenarios could theoretically birth naked singularities. Take a rapidly spinning black hole known as a Kerr black hole. Spin it fast enough, so close to light speed that its event horizon stretches thin, and the singularity might peek through like a prisoner slipping past a crumbling wall. Alternatively, if two black holes collide in just the right way, their merged event horizon might temporarily fracture, exposing the singularity for a fleeting instant before resealing. Even the collapse of exotic matter, hypothetical particles with negative energy, could forge a naked singularity from the start, bypassing the need for an event horizon entirely. Why does this matter? Because naked singularities wouldn't just break cosmic censorship, they'd rewrite the rules of predictability. Near a traditional black hole, the event horizon ensures that whatever happens inside stays inside, preserving the universe's orderly cause and effect relationships. But a naked singularity would unleash gravitational anomalies, closed time-like curves, fancy jargon for potential time loops, and other phenomena that make physicists wake up in a cold sweat. It's like removing the containment field from a science experiment. Suddenly, anything goes. The debate rages because no one's ever spotted a naked singularity, and for good reason. If they exist, they'd be nearly indistinguishable from black holes at a distance, their telltale signatures buried in chaotic gravitational waves or twisted light patterns. Some theorists argue that quantum gravity effects, still poorly understood, might naturally prevent naked singularities from forming, acting as a microscopic bouncer that keeps singularities clothed. Others counter that the universe might allow them in rare, extreme conditions, like cosmic glitches in an otherwise orderly system. For now, naked singularities remain in the realm of pencil and paper physics, a tantalizing "what if" that challenges our assumptions. But their very possibility forces us to confront how little we truly know about gravity's extremes. If they're out there, lurking in the cosmic dark, they'd be more than just astronomical oddities. They'd be proof that even the universe's strictest rules have loopholes. And that's a revelation worth tearing down the curtains for. Near the supermassive black hole at the heart of our galaxy, stars don't glide in serene, predictable orbits. They careen through space like drunken fireflies, tracing wild, looping paths that defy Newtonian physics. Astronomers tracking these stellar daredevils have uncovered a celestial ballet of chaos, where gravity doesn't just tug, it whips objects through spacetime at a quarter the speed of light. The star S2, for instance, doesn't orbit Sagittarius, a star in a neat ellipse. Instead, it slingshots around the black hole in a rosette-shaped spiral, its path precessing with each revolution like a spirograph gone berserk. This isn't celestial disorder, it's Einstein's general relativity playing out in real time, proving space isn't just curved, it's a roller coaster. The secret behind these chaotic orbits lies in extreme gravity's grip on spacetime itself. Close to a black hole, space becomes so warped that a star's trajectory doesn't close into a repeating loop. Instead, the orbit rotates slightly with every pass, tracing a new segment of what physicists call a Schwarzschild precession. Picture a vinyl record with the needle skipping grooves. Each revolution lands the star a little ahead of where classical physics predicts. The effect is subtle in most cosmic settings, but near Sagittarius, a star, it's glaringly obvious. When S2 made its closest approach in 2018, telescopes caught its light redshifting and blueshifting dramatically as it accelerated to 8,000 kilometers per second, so fast that relativistic time dilation made its clock tick measurably slower than ours. But S2 isn't the only performer in this gravitational circus. The star S62 completes an orbit in just 9.5 years, an absurdly short time given the black hole's 4 million solar mass heft, reaching speeds that shatter solar system records. Even stranger is S414, which dances so close to the event horizon that its orbit is essentially a high-speed game of chicken with oblivion. These stars aren't just cosmic curiosities, they're precision instruments. By mapping their frenzied paths, astronomers have confirmed general relativity's predictions with unprecedented accuracy, all while ruling out alternative gravity theories that can't explain such extreme orbital gymnastics. The galactic center's stellar zoo holds darker surprises too. Some stars, like the bizarre G objects, look like bloated gas clouds but move like compact stars, possibly the mangled remains of stellar collisions catalyzed by the black hole's tidal forces. Others, like the star S0102, follow such eccentric orbits that they may have been flung into their current paths by a long-ago interaction with a second, now-vanished black hole. These chaotic dynamics aren't random. They're clues etched in starlight, revealing how supermassive black holes sculpt their surroundings over eons. What makes these observations revolutionary isn't just their confirmation of Einstein's century-old equations. They're a live demonstration of how black holes engineer their galaxies. The same gravitational forces that twist stellar orbits also funnel gas clouds toward the abyss, fueling quasars and regulating star birth across entire galaxies. Every erratic loop, every relativistic shudder in a star's motion, is a thread in the grand tapestry of cosmic evolution, one where black holes don't just lurk in darkness but choreograph the dance of the stars themselves. Black holes might be more than cosmic dead ends. They could be the ultimate cosmic midwives, giving birth to entirely new universes with their own laws of physics. This mind-bending idea, championed by physicist Lee Smolin, flips the script on everything we thought we knew about these gravitational giants. Called the fecund universe theory, it suggests that every time a black hole collapses, the extreme conditions inside could trigger the birth of a whole new cosmos hidden within the singularity. And here's the wildest part: these baby universes might not play by our rules. Their physical constants, the speed of light, the strength of gravity, even the charge of an electron, could be slightly tweaked, creating realities utterly alien to our own. Picture the singularity at a black hole's core not as a dead end, but as a cosmic pressure cooker. Under such unimaginable density and heat, spacetime itself could undergo a phase transition, like water turning to steam, birthing a new universe in the process. This fledgling cosmos would inflate rapidly, connected to ours only by the narrowest quantum thread, the black hole's event horizon. From our perspective, nothing escapes. But from inside, it's the Big Bang all over again, with one critical difference: the fundamental constants governing physics might shift slightly during the transition. Gravity could be stronger, the weak nuclear force weaker, or matter might behave in ways we can't even imagine. Why would nature allow such a thing? Smolin's theory proposes an elegant, almost Darwinian logic. Universes that produce more black holes would, in turn, spawn more offspring universes. Over cosmic time, this would favor physical constants that maximize black hole production. It's natural selection on a multiversal scale where the fittest universes, those best at making black holes, dominate the cosmic family tree. Our universe's finely tuned constants, from the cosmological constant to the mass of the proton, might not be lucky accidents. They could be the result of eons of cosmic replication, optimized for black hole fecundity. The implications are staggering. If true, our universe could be one of countless iterations in an unending lineage, each tweaked slightly from its parent. Some might fizzle out instantly, their constants too unstable for structure. Others could thrive, giving rise to black holes and thus new universes in endless cycles. It's a fractal vision of reality, where every black hole is a potential doorway to another cosmos, its physics subtly reshuffled. Critics argue there's no way to test this idea. After all, we can't peer beyond a singularity. But hints might lie in the statistical quirks of our own universe. If black holes are cosmic seeds, we'd expect physical constants to cluster around values that favor their formation. Curiously, that's exactly what we see. Even the cosmological constant, which drives the universe's expansion, is oddly balanced, large enough to allow galaxy formation, and thus stars and black holes, but small enough to avoid tearing spacetime apart before they can spawn. For now, Smolens's theory remains speculative, a thrilling what-if at the edge of cosmology, but it challenges us to rethink black holes not as endpoints but as potential beginnings. Every collapsing star, every merging binary, every supermassive beast at a galaxy's heart, each might be writing the first chapter of a new cosmic story, one where the rules are just different enough to surprise even the universe itself. For all we've uncovered about black holes, their gravitational might, their space-time warping tricks, even their haunting songs, we've barely grazed the surface of their deepest secrets. These cosmic enigmas are less like solved puzzles and more like ancient manuscripts with half the pages still missing. Take the information paradox, one of physics' most notorious standoffs. On one side, quantum mechanics insists that information can never be destroyed. On the other, black holes seem to erase it completely when matter crosses the event horizon. Stephen Hawking's radiation theory offered a glimmer of hope, suggesting information might escape encoded in particle pairs, but the devil's in the details. How does scrambled data unscramble itself? Does it cling to the event horizon like a hologram or tunnel through wormholes we can't yet see? Decades later, physicists are still wrestling with these questions, and every proposed solution opens 10 more. Then there's the elephant in the room, quantum gravity. Black holes are where Einstein's relativity and quantum mechanics crash into each other with catastrophic elegance. Relativity paints them as smooth, predictable warps in spacetime, while quantum mechanics demands a frenetic, probabilistic reality at their cores. Bridging these theories would rewrite physics, yet black holes guard their secrets fiercely. Even our best attempts, string theory's vibrating filaments, loop quantum gravity's spacetime atoms, feel like sketching a rainbow with charcoal. We know the colors are there, but the tools to reveal them remain just out of reach. Consider the wild cards we've barely begun to probe. What happens inside a black hole? Is the singularity a true infinity, or does quantum physics soften it into something stranger, a Planck star, a fuzzball, or a portal to another universe? And why do some supermassive black holes, like Sagittarius, a star, nap so quietly while others devour galaxies in a blaze of glory? Even the black holes we've seen through gravitational waves and event horizon telescope images are cosmic icebergs. We're glimpsing the tip while the bulk lurks in darkness. The most thrilling part, every answer we chase reshapes the questions. Dark matter could be primordial black holes. Naked singularities might defy cosmic censorship. Black holes might not even be holes at all, but time-reversed white holes in disguise. Each theory is a thread in a tapestry we're still weaving, one observation at a time. So while we've mapped their shadows and heard their collisions, black holes remain the universe's ultimate cliffhanger. They're not just objects, they're conversations between gravity and quantum mechanics, between creation and destruction, between what we know and what we've yet to imagine. And somewhere in that dialogue, the next revolution in physics is waiting, hidden in the dark. From cosmic time warps to self-devouring jets, black holes have shattered every assumption we've ever had about the universe. They're not just celestial oddities, they're the ultimate rebels, bending the rules of physics until they snap. Imagine objects so dense they make light orbit them like a trapped firefly, or collisions so violent they shake the fabric of spacetime itself. These gravitational titans rewrite the laws of reality with every discovery, whether it's Hawking radiation proving they're not eternal, primordial black holes potentially hiding as dark matter, or the spine-tingling possibility that each one could be birthing an entirely new universe behind its event horizon. Think about it, black holes taught us that time isn't universal. It slows to a crawl near their grasp. They've shown us gravity's true power, not by sucking matter in, but by whipping stars into frenzied orbits and launching jets of plasma across galaxies. They've whispered their mergers to us through gravitational waves, sung their screams in X-rays, and even flirted with the idea of being cosmic portals. And yet, for all we've learned, the biggest mysteries remain. What lurks inside a singularity? Do black holes truly erase information, or are they quantum librarians encoding it in ways we can't yet decipher? The deeper we look, the more they reveal how much we still don't know. This journey through 30 mind-bending facts proves one thing: black holes aren't just astronomical objects, they're the universe's grandest experiment, testing the limits of human knowledge. Every observation, every theory, every paradox they present is a puzzle piece in understanding everything from the birth of galaxies to the fate of reality itself. So what's your favorite revelation? Was it the black hole that spins space-time like a whirlpool, or the eerie possibility that we're all living in a universe spawned by a singularity? Drop your thoughts in the comments and let us know which cosmic mystery we should explore next. The universe is full of wonders, but black holes, they're the dazzling, terrifying proof that sometimes truth really is stranger than fiction. Now go blow someone's mind with what you've learned today. The cosmos is counting on you.